Chemical reactions. Chemical reactions occur when bonds are formed, when bonds are broken, or when a substance is changed into another substance. Inside the body, we often call this metabolism. An example of metabolism would be when food goes into your mouth, it's going to begin to be broken down or changed into another substance. It will then go into your stomach and through your digestive tract, and your body will obtain energy from that food. Here's an example of a chemical equation. On the left, we have the reactants. This particular chemical equation is respiration. So on the left, we have sugar plus 6 oxygen. That arrow in the middle is called yields. It means that some kind of an action is occurring. And then on the right-hand side, we have the products. 6 carbon dioxide, 6 water, and energy. And for this particular equation, this ends up being the useful product, this energy, because this is what your body is using to do other life processes. Subscripts and coefficients. A subscript is the number of atoms of each element in a molecule. For example, this is sugar or glucose. There are 6 carbons, 12 hydrogens, and 6 oxygens inside this compound. Now, the coefficient is different. The coefficient is going to go before the total, and it basically says how many copies of the molecule or the element or the compound do I have. So you can see that there's no number here. So there's always a number 1. We just don't write it. So it means we have 1 sugar compound, but we have 6 oxygen molecules. We also have 6 carbon dioxide molecules, 6 water molecules that lead us to some amount of energy. So here's another picture. We have this 12 here. This means 12 copies of the water molecule. So literally 12 water molecules. Now, if you want to count actual atoms, that's where the subscript comes in. There may be 12 water molecules, but there are 24 hydrogen and 12 oxygen included in the 12 molecules. Coefficient, how many copies of the item do I have? Subscript, how many of that particular element do I have? So again, how many atoms of hydrogen are there in 12 water molecules? 24. Water is an incredibly important substance for life. There's a reason that it's called the universal solvent, and this is because it's really good at breaking things down. It's also really good at providing the habitat or the home for chemical reactions to take place. Now, water is a polar molecule. This means that even though the whole molecule is neutral, portions of it are positive and portions of it are negative. The reason for this is that hydrogen is a tiny little atom, and it gets bullied a little bit by the oxygen. They form a covalent bond, but when they form a covalent bond, the hydrogen just gets custody of those electrons a little bit less often, so they're positive. The oxygen gets custody of those electrons a little bit more often, so it's negative. But remember, +1 -1 is neutral. +1 -1 is neutral, so the overall compound is neutral. It's just different areas on the compound are positively or negatively charged. Water's density. Water has this really specialized property, and that is that it becomes less dense as it freezes. You know this. If you put a piece of ice into water, it floats. This doesn't happen for most items. Most items, as they get colder, they get more dense. And so the reason that this happens is that when water freezes, it forms a crystal structure. that crystal structure has spaces between the atoms, and those spaces between the atoms are larger than in its liquid form. And so the overall density of ice is less than 1 gram per milliliter squared or cubed, excuse me, and so it floats on that liquid water. Polarity. Water is polar. Remember when I said that they were going to share electrons? They share electrons, but they don't share them equally. The hydrogen gets bullied out of their electrons more often, and the oxygen has those electrons more often. Thereby, oxygen is negative and hydrogen is positive. But again, the overall compound is neutral. Water also engages in hydrogen bonds, but these are the bonds that are between water molecules, okay? And they're a weak covalent bond. So in other words, because the molecule is polar, the hydrogens within the molecule form strong covalent bonds with their parent oxygen. But because, remember, this is a little bit negative and this is a little bit positive, they form weak hydrogen bonds. Hydrogen bonding. Due to polarity, water compounds are attracted to one another. The slightly negative oxygen attracts the slightly positive hydrogen. This attraction among water itself is called cohesion. But water is also attracted to other materials. You can see this in the meniscus that forms in a graduated cylinder. And so that is called adhesion. The way that I like to remember this is when you add water plus glass, you get adhesion. The water is attracted to the glass. Cohesion is the other one. Water is attracted to itself. An example of this would be when you go outside in the morning and there's little droplets of water, balled up on a leaf. The water is more attracted to itself than it is the leaf, hence it forms that domed structure. Here is a picture of what's going on. Remember, this little squiggle here means partially. The hydrogen is partially positive, covalent bonded to the partially negative oxygen. The hydrogen bonding occurs between 2 or more water molecules. Hydrogen bond, covalent bond. Strong bond, weak bond. Here's a picture of how cohesion forms a specialized item called surface tension. So these water molecules are weakly attracted to each other. In other words, they're kind of pulling each other in. Where those water molecules transition to another substance, usually air, they're much more attracted to each other than they are to the air that surrounds them, because usually the air around it are in these really strong covalent bonds. Diatomic oxygen, diatomic nitrogen are the two most common, or some noble gases like argon, neon. They don't like to bond with anything, and so the water is really attracted to itself, and it forms this surface tension. This is why animals like water striders are able to stand on the surface of water. So here's an example of that. Look at this little guy. Look at his feet. He's literally standing on these hydrogen bonds that are formed between water molecules. Look over here. Look at how this water is lumped up on this leaf. It means that the water likes itself more than the leaf and more than the air surrounding it. Adhesion. Adhesion is a little bit different. Adhesion means that the water is attracted to other things. So how that happens is a thing called capillary action. This is actually how plants get water up from the ground against the force of gravity. So when I have these celery stalks, or when I have these plants, if I put some food coloring in, that food coloring is going to travel with the water up the celery, and it's going to actually change the color of the celery stalk. So adhesion, I add water to a plant, and the water is attracted up that plant via capillary action. Now remember, water is the greatest solvent on earth. It loves to dissolve other items. So for example, if I have sodium chloride and I put that sodium chloride into water, the water will rip that sodium chloride apart. It will dissolve it. In other words, I will end up with salt water. Same thing happens with sugar. If I take my sugar and I put it into my tea, what I end up with is then going to be sugar water because the water dissolves those other substances. Now, sometimes things don't actually dissolve. They become what we call mixtures. A mixture is composed of two or more elements that are physically mixed but not chemically combined. In other words, look at these M&Ms. They may be different colors, but they're not chemically combined. There are two types of this, a solution and a suspension. A solution. In a solution, you're going to have solvent. This is usually going to be water. And then you're going to have solute, the thing that is dissolving inside the water. Usually, this will end up looking like just a plain, an item that looks the same throughout. For example, if I take salt or sugar and put it in water, it will evenly distribute out through the water. How do I remember these? It's tough. You see this word solvent? It has more letters. It has 1, 2, 3, 4, 5, 6, 7 letters, whereas solute only has 1, 2, 3, 4, 5, 6. So I remember that the solvent is in the greater amount because it has more letters, and the solute is in the lesser amount. That also helps me remember that the solvent is water and the solute will be something else. Suspension. Suspensions are really interesting. The item goes into the mixture, but it doesn't necessarily settle out. Milk is an example of this. So for example, if you have milk and you shake that milk or you beat that milk with a paddle, what you end up doing is separating that suspension, and you get curds and whey or butter and that liquid milk portion. Your blood is also a suspension. You have red blood cells and white blood cells and platelets, all kinds of things in your blood, but it looks like one thing. But these items are not actually mixing together and they don't actually settle out. So they're a specialized form of a mixture where they're all together, but they don't settle apart. In this learning checkpoint, you should be able to answer these questions, but we'll take a look at that when we look at our study guide. Acids and bases. This next section is on pH. And the reason that we teach the former section is because I want you to be able to understand that water actually falls apart into two individual ions. So this H2O, this compound H2O, falls apart into a positive hydrogen and a negative OH ion. So in pure water, if you have just pure water, your number of H pluses will be exactly identical to the number of OH minuses. This is why we get water as the neutral pH of 7. The pH scale is called the power of hydrogen scale. And with the power of hydrogen, if you add more H pluses, you end up with an acid, which is something that is under the number 7. If you have more OH negative ions, you end up with something that is basic or something that is higher than the number 7. Now, pH scale is what we call logarithmic. What I mean by that is that if I have something that is at the number 1 and I go to the number 2, that acid is 10 times less strong, not 1 time. Or if I have something that is at the number 7 and I go to the number 8, that is 10 times more basic, not 1 time. Acids. Acids range from a 0 to a 6.99 on the pH scale. They are solutions that have more H plus ions. So in other words, more H plus ions than OH minus ions. The closer you get to the number 0, the more acidic the solution. This is going to be stomach acid or lemon juice. Bases or alkalines. They range from a 7.01 up to about a 14. And these are going to form OH minus ions in solution. So in other words, the OH part of water is going to be in greater number than the H plus. The closer to the 14, the more basic the solution is. Strong bases would be lye, bleach, and oven cleaner. Now, as you look at this pH scale, I want you to understand acids are not stronger or weaker than bases. If you're at the same position away from 7, you're going to end up with a similarly strengthed item. So in other words, a 0 acid will eat your skin and corrode things just as easily as a 14. So in other words, if I had, say, a piece of bologna and I put some acid on it, it's going to burn that meat product. If I come over here and put lye on it, it's also going to burn that meat product. And so the farther you are away from 7, the stronger. As I move in 1, this is 10 times weaker base. This is a 10 times weaker acid. Then from a 1 to a 2, 10 times weaker. From a 13 to a 12, 10 times weaker. And every time I make the jump in, my number of OH minus ions is getting more and more similar to my H plus. Remember, when I'm at a 7, my OH minus will exactly equal my H plus, and what I will have is pure water. pH in living things. Living things don't like to be wildly acidic or wildly basic. They generally like to be between a 6.5 basic and a 7.5 acidic. These are the optimal pHs for chemical reactions to take place in the body. Any serious switch in that is going to cause or could cause fatal problems. Now, luckily, if your body gets thrown out of proportion, you can use these things called buffers. Probably the one that you're most familiar with would be something like either milk of magnesia or Tums. And those are basic items. Think about it. You sit down to dinner. You have this amazing spaghetti dinner. Lots of beautiful, rich, tomato gravy. You eat it, but then all of a sudden your stomach doesn't feel so great because tomatoes are acidic. And when you ate all that tomato sauce, it made your stomach a little bit more acidic, and that stomach is starting to wear away your stomach lining. So you go to the bathroom, you take a couple of Tums, you wait a while, and the pH of your stomach normalizes. There's ways to do this with blood too, but it usually requires medication to make that pH change. Again, we'll cover a learning checkpoint in a Google form, but here are some questions that you should be able to answer from this lesson. Remember, I'm just going to run this one slide because all of these are in your chem study packet that's separate. Make sure that you're looking it over and that you're prepared for the Chem 1 test.